Right, it's 11:30, sorry, 9:30, and we are going to look at chapter 4.4 and chapter 4.5. And we will skip chapter 4.6, and so our next lecture will be on 4.7, improper integrals. 4.6 is not in the study guide. Right. So before we start looking at 4.4 and 4.5, we've got some unfinished business. So the question that we were looking at on Wednesday, we concluded that the graph should look like this, but there's something that we didn't discuss, which is a possibility that is there. So based on the information that we have, which is this, that it decreases to the left of 0, and then it increases up until 1, and then it decreases again, and then it increases. We end up with a possibility that our function might actually cut the x-axis, go down, and then maybe 2 f of 2 will be here, right? So that's another possibility, but we had said it doesn't cut it. It's somewhere up there. The graph would look like that. So I just want to discuss that a bit, maybe for the next 2-3 minutes, to show why it doesn't cut the x-axis, why it doesn't go down. Can you just confirm that you can hear me? I didn't ask that, so that I'm not talking to myself. Okay, great. So good morning, everyone, and welcome to our lecture. And so what we want is to prove that that big F doesn't cut the x-axis if x is greater than 0, and then we are then guaranteed of the graph that we had, which is something that looks like that, right? Where this is 2 f of 2, right? So in other words, for us to prove this, we just need to prove that f of 2 is greater than 0. So for us to do this, we sort of have to go into finding big F. Otherwise, we will not be able to do it. So for us to do that, we rewrite our rational function here. Let me use black. This in this form, and here we use long division. I'm not going to get into the details there, but just believe me that you can write this function like that. You will do long division in detail, I think, in chapter 6. So okay, so we can write this function like this, and so we've got f of 2. We want to find out what f of 2 would be, right? And so if we rewrite it like that, we've got t minus 3 plus t over t squared plus 1 plus 3 over t squared plus 1, like that. And we want to integrate this and see what happens. So once we have this, we can see that this becomes that, and then this becomes that. Yeah, so we should put 2 there. From 0 to 2, we get that, plus if we integrate this, we will have half of the natural log of t squared plus 1, the absolute value of that, from 0 to 2, and then plus 3 times arctan of 2. Here you can say arctan of t, and then you evaluate from 0 and 2, and then you get that. So if we evaluate here, we get minus 4 plus half the natural log of 5 plus 3 times arctan of 2, and this value if you punch it into your calculator just to see what's happening, you will see that you get approximately this this value there, and then 3 times this value, and if you add the 2, you see that they are greater than 4. So because we have a -4 there, it means this is greater than 0, and so therefore f of 2 is greater than 2. So when we look at our graph, it's indeed above there. And right, so we had to show that. And then there was a question on horizontal and vertical asymptote, and yeah, I didn't quite explain what happened there. So we ended up with a graph that looks like that, where this is the x-axis and the y-axis there, and that's 2, that's 1. So when we looked at the limit as x tends to infinity of f of x, we saw that it's going to infinity. And when we looked at the other side, we saw that this is also infinity. So here, what it actually proves is there is no horizontal asymptote and there is no vertical asymptote. The other possibility here, from here, we knew that from 2 going up, it's going to be increasing, but we don't know if it was going to go to infinity, or it could increase. Let me bring back. And instead of going up like this, it would maybe go somewhere like that. So it will still be strictly increasing, but maybe there is some value there that it doesn't pass, which would be a horizontal asymptote, right? And so in this case, we saw that because it's going up like that, there is no horizontal asymptote. Same applies to vertical asymptote. If we were to, it would still be increasing if it went like that, but maybe there's a value like that, some value, I'm going to call it what, C, such that even though it's increasing, it doesn't pass at C. And in this case, we see that as x tends to infinity and going to minus infinity, there's no problems of that sort. So because of that, we don't have a vertical asymptote and a horizontal asymptote. We will, I think the next chapter, chapter 5, you do curve sketching, you do this in much more detail. But just to preempt that, that was the explanation of no horizontal or vertical asymptote there. Right. Okay. So that was that. And if you didn't watch the video from Wednesday, I sort of went on to prove this. So feel free to go back to the video and watch that part of how to prove this. Right. Now let's get into chapter 4.4 or section 4.4. And here we want to talk about the integral mean value theorem. So you know the mean value theorem from 114, and we are going to do that one is for so we are going to look at the one for integration, right? So but before we do that, we are going to have something which is the average of a function. So we already know how to find average of numbers, right? If you have got a set of numbers and then you want to find its average, you just take the sum of all the numbers in that set and then you divide by the number of the cardinality of that set. And so what we want to answer in this part is what is the average, what is the average of a function y is equal to f of x on some closed interval a b, right? That's really the question we want to answer. And just to sort of show you what we are trying to see is, suppose you've got an a there. Maybe let me just put a solid line, and then you've got a function which we are calling y is equal to f of x, and then okay, maybe let me draw it with a bit more like that. Okay, so suppose this is our function, and we want to check what's happening there. So what we would call the average of this function would be something like that. And just to sort of, this is a rough sketch, so it's not going to be accurate, but the point there is, if I am to, if this is indeed the average, this point, if I draw that line, if that is the average of this function from a to b, what it would mean is, if I take this space and that space, edit, and then take that space from there, the bottom part there, and add, it would mean that the green area would be equal to the red area. So you sort of even out the bottom part and the top part of that, and then you've got an average. Right. So how do we find the average of a function? That is our question there. And such that what I've said happens, where the green area is equal to the red area. And so what we are going to do is, we are going to subdivide AB into n equal subintervals. That's the first thing. And then we can label these points x naught up to xn. So if we do that, we'll start with a being the x naught, and then we have our x1 there, and then x2 there. I mean, there'll be equal parts, but this is just a sketch. So, and then we have got the last one. So we've got x1 and then xn, right? So we would have divided them into n equal parts like that. And then if we take a point, so we take a point on each sub interval that we have. So that means we've got n points. Then if we want to find the average, it will be approximately equal to 1 over n times the sum of these points, right? So if you go, for example, here, if you take some point between this sub-interval, you get this value that we are calling f of xi star, x1 star in this case, and then you go to the next, and then you take another point. So we are sort of taking the middle point as we go. And so if we want to find the average, we just divide by n, and then we get a formula like that. But this can be written as this times b minus a over b minus a. And here we're just putting a convenient one, so we are not changing anything. and f k star like that, right? And then from here, we can then rewrite this as, if we take b minus the denominator here, and then we put everything else after the sum sign, then we have something like this. So if you think about what we have from A to B, if you think about it as L, like the length between A and B, then it will be B minus A, the size of the interval, size in quotes. And then if we think about each interval now, each sub-interval, we are going to say, since they are equal, we are going to have B minus A over N, right? So each sub-interval is that size. So we are going to use this notation to represent each sub-interval. And so we can rewrite this as, so if you think about this, we can call it delta of x there, and then we get 1 minus b minus a times the sum of that. And here we are trying to make some Riemann sums of some function, and then we use integration. So we can rewrite it as this, right? These are the so we end up with these Riemann sums where this point that we took is in between this interval, right? So the average, so our estimate here, remember we are approximating, right? The approximation is going to depend on the number of points that we pick, how we subdivide n, right? So if we have got more n's, then our average, whatever approximation we are doing, will be close to the average, right? And if then n goes to infinity, then these become very small until we sort of get to the actual average. You'll see that as n tends to infinity, this just becomes the integral of f of x dx, if you remember when you were looking at Riemann sums. So these will be Riemann sums of this. So as n tends to infinity, we end up with that. And that gives us our definition of the average of a function. So for a function f, so we've got that function that is integrable. So this is quite important in this case. Then the average value of f on the interval, that is going to be given by f a v is equal to 1 over b minus a, the integral of from a to b of f of x dx. So that's how we find the average. So it's straightforward. If you're asked to find the average, you just use this formula and then you get your answer. So let's look at an example. So let f f of t be defined this way. So it's 3t squared if t is from is between 0 and 1, inclusive of 1, and then 2t plus 6 if this is between sorry, not 0, it should be 1. If t is between 1 and 2, we define it like that. Right, so now we want to find the average of this. So find the average of the function there. And for us to do that, we will use our formula. So we will use the definition there. So it's going to be 1 of b minus a of a from a to b of f of t dt, right? And this is equal to 1 over 2 minus 0. If you look at the interval here is 0 to 2. If you that's where f of t is defined. So we've got 1 over 2 minus 0 of from 0 to 2 of f of t dt. And if we look at it, we can see that it's defined in these cases, so we sort of have to separate. So we get a half coming from there of the integral from 0 to 1 of f of t dt plus half from 1 to 2 of f of t dt, like that. And then we say half from 0 to 1 of f of t. From 0 to 1 is 3t squared, so we put 3t squared there. And then from 1 to 2, it is 2t plus 6 dt. And from there, we just do our normal integration. So we get t cubed from 0 to 1 plus half. If we integrate that, we get t squared plus 6t from 1 to 2. And if we evaluate, we get half minus 0 for the first one, and then plus half of 2 squared plus 6 times 2 minus 1 squared minus 6 times 1, like that. And if you evaluate this, you should get 5. So we get 5 as our average for this function, right? Now, one question that can be asked is this: is there p between 0 and 2 such that f of p is equal to our average of the function? And in this case, it is a no. So the answer is no. And the reason, let's look at why it is going to be no. So we have to deal with our cases based on the intervals. So we've got 2 intervals. We've got a case where p is from 0 to 1. And then we've got when p is from 1 to 2. And in this case, if you calculate, I'm not going to do the calculation. You can do that. So if p is from 0 to 1, then if you put 0 there and 1, you will see that f of p is going to be between 0 and 3, right? Just put in the value from 0 to 1, you put 0 and then you put 1, and we can see that this function is increasing, so there's no problem there. So it's from 0 to 3. And then if you look at p less than element of 1 to 2, then you end up with f of p is between 8. So this one would be from 1. It doesn't include 1. So from 8 to 10. So in other words, f of p is going to be 1 on these intervals. And because of that, it means that therefore f of p is not going to be equal to 5, which we found here for any p that you pick. All right, and we are going to find out that this is not the case with some special functions. Right, so there's a question, do we have to show that the function is integrable? First, no, you don't have to, because by doing this integration here, so you just have to notice if it's integrable or not, right? But otherwise, by doing this, we are already showing that it's integrable. I hope that clears that. Because if you are able to find the integral, then it means it's integrable. And then there's another question. So just confirm if that clears that. And then another question from Rutendo. So if the function is piecewise defined, is the answer to B always going to be no, or we have to check? You have to check, because it might happen that in the case that you're dealing with, you can find the value of P. So it's not always true that it's going to be a no. In some cases, it might be a yes, but in this case, it's a no. And one thing you need to notice in this on this function is that so note that the function that we are dealing with is not continuous, right? If you look at 1, if you approach from the right and from the left, you can see that the limit will be different. So therefore, this happens when f is not continuous, but not always. So if you are given a question and you can see the function is not continuous, it doesn't necessarily mean that there's no p such that this happens. But we've got a guarantee when f is continuous. So and that leads us to our theorem, which is the mean value theorem. So the mean value theorem for integrals, or the integral mean value theorem. So you should remember the one for the derivative, because we need to use it in this, and it's in the appendix of the book, so you can go and check it out. Well, I'll probably write it soon. So if f is continuous, right, on AB, so that is important if you want to use this theorem, then there exists a number P in the open interval AB such that f of P is f of the average, which is equal to 1 over b minus a, the integral from a to b of f of t dt. Right, so the condition that we want is f is continuous. So if f is continuous, we are guaranteed that this happens. If f is not continuous, we don't know. We are not guaranteed. So it can go either way. Right, so let's look at the proof. And so let f of x be the integral from a to x of f of t dt, and this is for some x that is between a and b, and this should look familiar. So why is big F differentiable? And the answer is the small f that we have, we are told is continuous on AB. This is assumption in the statement of the theorem. So by the FTC, by the fundamental theorem of calculus, it follows that f is differentiable on AB. Right. So we know that f is f is differentiable on that. So the next step is we should be able to then apply the mean value theorem from 114. So why can we do that? So why can you apply the MVT, the mean value theorem? Let me just say in brackets from 114 of big F on the closed interval AB, right? Why can we do that? The reason is F is continuous on AB, and that's coming from the fundamental theorem, right? If you look at this, we know this is what happens if small f is continuous, and then we know that f is differentiable on the open interval that. And again, this is coming from the fundamental theorem of calculus. So what it means is both conditions of the MVT of the mean value theorem are true, right? So we can use it. We can use it, right? Just to remind you what the theorem says, so you can go and look it up. It's in the appendix. So 8.1.9 MVT. So it says, suppose you've got a function f which is continuous on the closed interval AB and differentiable on the open interval AB, then there exists some C such that f prime of C is equal to f of B minus f of A, right? So this is the MVT. So we have shown that big F is continuous and is differentiable on those respective intervals. Then we are guaranteed of this, but we want to collect that information to say what. So if this is big F, what is big F prime and what is f of B and all that, right? So let's see what we have. So big F, because here we are trying to apply it on big F, so we want to collect all that information. So what is big F of A? It is going to be the integral. By definition, it's going to look like this. And because we've got the lower bound equal to the upper bound, we know that that is a 0. So here we are going to put 0 because we can see that's what happens. And then f of B is just going to be the integral from A to B, f of t dt. We don't know what it looks like, but so we can leave it like that. And then if P is an element between A and B, we know from the FTC that f prime of P is going to be equal to f of P, right? So we've collected all the information. We know that if we've got this value, then we can then we know its derivative. For any P that you pick, this we know what happens. Now we can use our MVT. So this is the last part. So by the MVT, there exists a P in AB such that f of P is equal to f prime of P, which is f of B minus f of A over B minus A, right? And we know that this is f of B, which is what we have there, minus 0, which is what we have there, over B minus A. And if we rewrite that, that's just 1 over B minus A, the integral from A to B of f of t dt. And that is the end of our proof. So we've used the MVT to find this integral version of it. So whenever you have a function that is continuous, you know that you are going to find this P such that that happens. Let's look at an, I'm going to give you homework. So let f of x, you can also look at the homework in the textbook, the example in the textbook to do this. So suppose you've got that which is defined between 1 and 3, the interval 1 to 3. So you want to find all points P such that f of P is the average. So here let me just point out that the theorem tells us that we are guaranteed of at least one P that does this, but there could be more. In fact, if you look at this example, you might see that you will find more P's that will have this property. Right, so that's that. So that is the end for the mean value theorem for integrals. Now let's go on to, let me start on a new page, chapter 4.3, which is arc length. Right, so what we sort of want to determine when we are thinking of an arc length is, suppose you've got a function. Let me just write it in this way. So suppose you think of an ant which is walking along some path which is a parabola. Y is equal to x squared, and it's moving from the origin to 1, 1. How many units does it cover? Units did the ant walk? Right? And so, I mean, if you've got a straight line, it's easy to find out what the length is, right, of a path. But if you've got something like this, which would be our function here, y is equal to x squared, right? How do we find out what is the length from there to there? That's the question that we are asking, right? And more generally, we can consider a curve C, which is defined like that. So it's along this interval, and oh, sorry, thank you, Rutendo. It's supposed to be chapter 4.5. I don't know where I got 4.3 from. It's 4.5. Thank you for that. Right, so we've got that, and so if we draw the curve, so suppose it looks like this. We've got A there, we've got X, and then we've got B, right? And so this point would be like X, f of X, so it will be a vector in that vector form. So what the question is, what is the length at any point? So if you think of any point, in this case, I picked this x there. What would be the length? So if we think of x here, what would be the point there? If we go there, what is the length in general? And so that means we sort of need a formula to be able to do this, right? So how do we derive our formula to be able to find out what is the length? And that's the next part. So to find the formula, we again divide AB into equal n equals subintervals. Subintervals. So let me just draw what we have. So we've got our function like that. It's not a nice one, but so we start at A, and then we end at xn, which is equal to b, and then the last one xn minus 1, and then we've got x1, x2, and then we've got in between we've got xi plus 1, right? And so the point here would be a vector p naught, vector p1, vector p2, vector pi plus 1, pn minus 1, and then pn, where what we are calling vector pi is the point xi, f of xi. So it's written in vector form like that, right? And then so for us to approximate what the value is, we sort of have to say, let me use yellow. We can find the distance like that, and then we go on like that. So I'm just drawing straight lines there, because that's how we estimate what the exact value is. So the exact value, we don't know it, but we can estimate using the distance between these intervals, and then we get something, right? And if you think about that distance, you'll see that, for example, if you think of P1, P0 to P1, right? The distance there, if I call it D, it will just be the norm of that, the norm of the difference there, and then we get what we need, right? So to then approximate the arc length, we can then say this is approximately equal to k is equal to 1 of n of these norms, pk minus 1, like that. And what is this? This is just, if we think about it, we can say this is xk minus xk minus 1, and then the other component is f of xk minus f of xk minus 1, like that. And this is equal to the square root of xk minus 1, sorry, xk minus xk minus 1 squared plus f of xk minus f of xk minus 1, and all that squared, right? That's how we find the norm of a vector like that. Right, and we know that for each k that we pick, f is going to be continuous on the interval xk minus 1 xk, and f is also differentiable on that open interval like that. So we know by the MVT, by the mean value theorem, it means that there is some point on the interval that is going to give us the average, right? Such that f prime of xk star is going to be equal to that over xk minus 1, sorry, xk minus 1, like that. So if we say the difference between these small intervals is delta, then what we get is that f of xk minus f of xk minus 1 can be rewritten as delta x times f prime of xk star, like that. And so therefore our arc length can be rewritten as the sum of from k is equal to 1 up to n of the square root of delta x squared plus delta x squared times f prime of xk star squared. So if we just substitute what we have here with this, we end up with something like this, and our delta there. And then we can then say, well, we can take out delta squared, so we can say this is 1 plus f prime of xk star squared times the square root of delta x squared, like that. And we end up with k is equal to 1 n 1 plus f prime xk star squared times delta x. If we take the square root of that, we get that. And then so these, remember, these are just Riemann sums of which integral? So if we let n go to infinity, we will see that the arc length is equal to the integral from a to b of 1 plus f prime of xk squared. No, we no longer have k's, right? So we've got x there times delta x. Sorry, what am I saying? F prime of that dx, not delta x. And so therefore that gives us our next definition. If f is that to r be a differentiable function, so differentiable on the closed interval that, and then assume that f prime is continuous on the closed interval AB, then the length of the curve y is equal to f of x, where x is between that, is going to be L, which is the integral from a to b of 1 plus f prime of x f prime of x squared dx, like that. And so this is this formula, that's all you need to know for this section, this formula. And let's just look at an exercise. We've got f of x, which is 2x cubed, x to the 3 over 2 plus 1, and we know that we are told x is greater than 0, and then let L be the curve C, where y is equal to f of x, and we want this interval. What is the arc length? What is the arc length? And so we are just going to apply this this formula that we have. What is the arc length in this case? And so we know f of x is like that. And then if we differentiate that, we get this is going to be 3x to the half plus 0, which we can rewrite as 3 times root x. So L will be the integral from 1 to 3 of 1 plus 3 root x squared, and we want the square root of that dx, right? And this can be rewritten as that. If we simplify here, we get 1 plus 9x dx. Right. So there are several ways of thinking about this, but you can follow what is in the textbook, but I'm going to do a different one. So if we let u be equal to that, then we get this, which is the root of u, right? And then du over dx would be equal to 9 dx. So that means 1 over 9 du, 1 over 9 du is equal to dx. And if we need to change our bounds, we need to change our bounds since we have done the substitution there. So this gives u is equal to 10 if you evaluate, and x is equal to 3 gives u is equal to 28. So we end up with this being equal from 10 to 28 of the root of u 1 over 9 du. And if you evaluate that, so 1 over 9, we can take it outside the integral sign, and we get u to the half du. And let me just finish. Then if we integrate this, we get 2 over 3 u to the 3 over 2, like that. And then we can then put our 28 and 10, and we get that this is 28 root 28 minus 10 root 10, and that is our solution. And so that's how we do this. We just use this formula there, and then we use the techniques that we have developed, whether we need integration by parts or whatever we have done, or even techniques in 114, we can use them if need be. And that is all that I have. Thank you. If you have questions, I'll stay behind for a bit. Otherwise, enjoy the rest of the day and your weekend. See you on Monday on chapter 4.7. You may leave if you need to. Otherwise, if you have questions, I'm still here for a minute or so. Thank you. All right, it seems that there are no questions. So thank you. Enjoy the rest of your day and the weekend. Bye.